first, we lost a whole day last week, and so and that got me discombobulated. On top of that, I started out assuming that I could move at 3 times the speed that I should have assumed that I could move the week before. And so I did some things very quickly that I'm going to review right now. And then I stopped and said, no, I've got to do some mathematics first. Okay, so I'm now returning to where I was a week ago Monday. And I'm going to pick up now and start doing the physics that I was doing a week ago Monday. So let's suppose that I have, in curved space-time, I have a particle that's moving along a world line. We can talk about this abstractly. So the world line is a point in space-time as a function of tau, where tau is the proper time ticked by an ideal clock that the particle carries. So this may be p of 0, p of 1, p of 2, and the curve itself is p of tau. The tangent to the curve is the particle's 4 velocity. And this tangent is dp d tau when it's written in a notation that I rather like when I'm not trying to be a mathematician, or it's the same thing as the derivative with respect to tau along that world line when you think of it as a directional derivative. It's interesting to look at the square of the 4 velocity. In order to do that, I'm going to, just for notation purposes to make this really clear, I'm going to put a little vector on top of here. This dp d tau is defined by the limiting process, as I've done before, which is the limit where you take the difference between 2 points that lie in the manifold that are close enough together that you can actually draw a vector that lies in the manifold. Take that difference between the 2 points and divide by this little tiny d tau, okay, and take the limit then. Okay, so u then squared looks like dp dot dp divided by d tau squared. And this dp is some little vector in here reaching from one point to another. And the way we define the metric, the squared length of this vector is precisely the square of the proper time that it takes in going from the tail of the vector to the tip. That was how we defined the metric, the very definition of the metric at the very beginning of the discussion, aside from a sign. And so this dp dot dp is minus d tau squared by the definition of the metric via the inner product. Now, so we have minus d tau squared over d tau squared, or we have minus 1, which guarantees then, without having introduced a basis whatsoever, it guarantees that the 4 velocity is a unit vector pointing in the time direction, as it should be from your prior experience working in flat space-time. The components of the 4 velocity in some coordinate system, the components are just dx alpha d tau, and I've discussed that previously for any curve. So the tangent to the curve, u alpha defined in this way, has components in this coordinates, in a arbitrary coordinate system that are just the derivatives of the coordinates themselves. Now, if this particle is freely falling, freely moving, with no forces on it other than those associated with space-time geometry, other than those associated with gravity, then it must, by analogy with what happens in flat space-time, it must then move along a straight line. It must move along a line that is the straightest line you can have in the presence of the space-time curvature. Or to put it differently, another way to say it is that it should parallel transport its own 4 velocity along itself. And this is called the geodesic equation. And you recall that what this really means is that if I go into a local Lorentz frame, the components of the floor velocity are held constant as you move a very short distance through a local Lorentz frame, just as they would be held constant if you were moving in flat space-time along a free fall trajectory. So that's a key aspect of physics in curved space-time. But what I would like to do now is to derive for you what this geodesic equation looks like in a coordinate system. So I go into space-time here and I introduce a coordinate system. And so there are coordinates like that. They're x alpha is a function of p, or p is a function of x alpha. And in that coordinate system, then the components of u are dx alpha d tau, as I've already discussed. And this derivative I can write, or this geodesic equation I can write as saying u alpha semicolon mu u mu is equal to 0. That's just this equation written in index notation. That is, I take a derivative along u of u. Okay. But the components of this gradient are u alpha comma mu plus gamma connection coefficients alpha mu nu u nu, and then I have a u mu. So this is just rewriting this gradient into which I've contracted the floor velocity in order to have a derivative along u. I've just rewritten this gradient in terms of a partial derivative now. This is a coordinate basis, so that's a partial derivative and a connection coefficient. So I can then collect terms and rewrite this. 0 is equal to u alpha comma nu comma mu u mu plus gamma alpha mu nu u mu u nu. Now let's look at this term here. I can rewrite this as partial of u alpha with respect to x mu, because this is a coordinate basis and that's what the comma means. And then u mu is dx mu d tau. You can now look at this as being a formula in differential calculus. And this formula in differential calculus is the formula is equivalent to simply the statement that this is equal to du alpha d tau. That is, you take a derivative with respect to x mu and then a dx mu d tau. That's how you would compute du alpha d tau. Okay. But u alpha itself is dx alpha d tau. So this is d by d tau of dx alpha d tau. And so I have a double time derivative with respect to proper time of the coordinate location of the particle. And each of these u mu's is a dx u d tau and dx nu d tau. And so I wind up in the end with 0 is equal to d squared x alpha d tau squared plus gamma alpha mu nu dx mu d tau dx nu d tau. And this then is a set of 4 ordinary differential equations for x0 is a function of tau, x1 is a function of tau, x2 is a function of tau, and x3 is a function of tau. There are 4 equations because there's one free index. Alpha can be 0, 1, 2, 3. So I have 4 ordinary differential equations coupled because of the connection coefficients for 4 unknowns. So this illustrates the fact that The fundamental underlying physics that one does in general relativity, or in any other field for that matter, typically involves geometric relationships that can be written down without any coordinate system, such as this statement that u is parallel transported along itself. But when you introduce a coordinate system, you can convert such things into, in this case, differential equations that you could go in and you could solve in order to find out the details of what the shape of this world line is in some coordinate system, given appropriate initial conditions. And since this is a second-order differential equation, you would have to give, say, at tau equals 0, an initial position, an initial first derivative of the position, that is, an initial position and an initial four velocity, and then equations, the resulting world line, or the resulting values of these four functions would be completely determined. Any questions? Okay. Now, let me now go to geodesic deviation, which is the foundation then in a few minutes for the Einstein equations and then for gravitational waves. Suppose that I have two particles that are momentarily absolutely at rest with respect to each other, which means that their world lines in space-time, there's some time in space. In space-time, they are moving initially along absolutely parallel world lines. And then I discussed a week ago Monday that the fact that space-time curvature, which is the relativistic version of a tidal gravitational field, it's going to cause these world lines that are initially parallel ultimately perhaps to cross. And I described how we can quantify this by introducing a separation vector c, which reaches from one particle to the other. I have a four velocity u of this particle, say, and I'm asking that the particles be at rest with respect to each other initially, so the derivative along u of c is equal to 0. I also would like to define c in such a way that in the local Lorentz frame of this particle, c is purely spatial. That means that it's orthogonal to u. That is, in the local Lorentz frame, u points in the time direction, and c is purely spatial, so it points in a direction that's perpendicular to the time direction. So I'm asking that u dot c is equal to 0. And these are true initially. So at the initial point P, which I could also, let's call that tau equals 0 along this world line. So here's tau equals 0, here's tau equal 1, 2, 3, and so forth. But the second derivative of c along u is non-zero. And it's that second derivative that's telling us that, in fact, that these world lines are going to get pushed together by the space-time curvature. And there is a derivation in the reading that I'm going to give you for next week that involves manipulating some derivatives, basically, that enables you to discover that the del u del u c involves precisely the same Riemann curvature tensor as we introduced as quantifying the failure of these double gradients to commute. And so what this turns out to be is minus the Riemann curvature tensor. So it has 4 slots. This is a vector, so there's one slot has to remain empty here, so that will also be a vector. And I'm going to wind up sticking a u, and a c into the other three slots because I have three vectors over here, a u, and a c. I better not stick the two u's into those slots because this is antisymmetric in the last two slots, and I would get 0 if I stick the same vector into those two slots. So one of these slots had better get c, and by convention it's that slot, at least the convention that I use, and the u's go here. So this is called the equation of geodesic deviation. It describes how two geodesics that are initially parallel, start to deviate from each other as you move forward in time along the world lines, along the geodesics. Okay. Now, in a local Lorentz frame, of, let's call this particle A, the one on the left. Let me label them up here. The local Lorentz frame of particle A at this initial time tau equals 0, the four velocity of this particle has a time component that is 1, and it has spatial components that are 0. Now, you might think or might hope that what that would mean is that the components of this, and I want to look at the spatial components because it's the spatial components that are really telling me in this local Lorentz frame how the particles are moving together or apart. So you might expect that del u c, the spatial component, let's call it the j component, because u has this simple form, it's just the unit vector in the time direction. You might expect that this will just be d squared cj dt squared. Because you're just differentiating twice along that time direction. But this is a derivative along the world line, which means in the time direction of c. Well, you have to go in and do some mathematics to really work it out. And you have to understand something a little bit deeper about local inertial frames than I have yet introduced. So I'm just going to tell you now, and I will give you the foundations for verifying this in another week or so when I want to talk about accelerated reference frames. I'm going to build some mathematical tools for discussing accelerated reference frames. Why do I want to discuss them? It's because you live in an accelerated reference frame. You have chosen not to fall freely through the floor. And so living in your accelerated reference frame, you must have some way to describe that. And so I will carefully develop a description of accelerated reference frames in order to discuss Earth-based gravitational wave detectors. And when I do that, I will develop enough tools to discover that this formula, in fact, is true. Even though there are two derivatives involved here, and you might be concerned that curvature would do something funny. In fact, it doesn't in a local Lorentz frame. So this is a key. I'm working in a local Lorentz frame. And so that just reduces to a second time derivative of the j component of the separation is equal to minus r. The first slot was empty and it's named j now because this, I'm looking at a spatial component of it. And then I will have alpha, beta, gamma, u alpha, c beta, u gamma. But u points only in the time direction. And so, so this is minus r, j. This alpha has to be a 0 because u points only in the time direction. I'm summing over the alpha. Alpha equals 0, u0 is 1. Alpha equals x, ux is 0, and so that would give 0. Alpha y, uy is 0, and so forth. So this will be minus r, j, 0. C points in a spatial direction, and so I can turn this index beta into a spatial index. So R0k, I have a ck, And then u again points in the time direction, and its value of u0 is 1, and so I just get a 0 there. So to re-summarize what I have just argued it should be, in the local Lorentz frame of particle A, where one is watching particle B move in spatially with respect to particle A, that local Lorentz frame, the equation of geodesic deviation has this form. Let's suppose now that this is a local Lorentz frame in a Newtonian situation. So we're in the solar system, for example, and the only gravity around is that associated with the planets and the sun and so forth, and we're treating it in Newtonian language. There are no gravitational waves to be concerned about. In a Newtonian situation, I derived a week ago Monday, I derived a formula for the tidal acceleration between two particles like this. And that formula said d squared cj dt squared is equal to minus e jk ck. Because this is a local Lorentz frame, the spatial metric is just the Kronecker delta. It's Cartesian. So whether I put indices up or down doesn't matter in a local Lorentz frame. Spatial indices. Temporal indices, it does. So you raise and lower a temporal index, you flip a sign. But raise and lower a spatial index and nothing happens. So I've used that to rewrite this in the form one normally does in Newtonian theory, where E has both of its indices down. So I have an index j down here, a j up there. It doesn't matter because I'm in a Cartesian spatial basis. Okay. And similarly here, I can just go in and I can lower this index with impunity because it's a spatial index in a local Lorentz frame. Compare those two formulas, and I see immediately that R, in a nearly Newtonian situation, the space-time components of the Riemann tensor are just equal to the tidal tensor. And I showed, when I talked about this before, that this was just the double spatial gradient of the Newtonian gravitational potential. So this exhibits explicitly in Newtonian situations the relationship between the Newtonian gravitational field and the Riemann curvature tensor. These are the pieces of the Riemann curvature tensor that will show up if you have two particles, they're at rest beside you, you're sitting in the space shuttle, for example, and the Earth's tidal gravitational field starts pushing them together or pushing them apart. It's these guys that will show up. It's the double gradient of the Newtonian potential, and it's the J0, K0 part of the Riemann tensor. Any questions? Okay. That's enough now to enable me to discuss the Einstein equations, or begin to discuss the Einstein equation. In Newtonian theory, the thing that determines the Newtonian gravitational field is a field equation that says that the Laplacian of phi is equal to 4 pi g rho, where rho is the mass density. Let's notice that the Laplacian of phi, that's the same thing as phi comma jk delta jk. So that's the same thing as ejk delta jk, or the same thing as ejj. It's just the trace of the tidal tensor. And so Newton's gravitational equation to determine the Newtonian potential just says that you take the tidal tensor, you take its trace, and that's equal to 4 pi g rho. And so you might expect then, by analogy, that in general relativity theory, what you would be asked to do is to take the trace of this Riemann tensor, and that should be equal to something like 4 pi g rho. That is, you would expect that the field equation should look something like Rj0 J0 is 4 pi g rho. That's a first guess at what the Einstein field equations ought to look like. Now, I'm going to get to the Einstein field equations within about 5 minutes. It took Einstein from 1912 to the end of 1915. 13, 14. It took him 4 years, okay? So we have made progress in the last century that we can do it very quickly, but there's a lot of arm waving if you do it this way, and he had a lot of struggle. Okay, so there is a fundamental problem with this equation, and the problem is that it really should be, if it's a real genuine physics equation that you really are going to have faith in, it should be a geometric frame independent equation. And this is an equation that's been written in a special coordinate system, the local Lorentz frame of some observer. And we've got to turn it into something that is a tensor equation then, a tensorial relationship between tensors. So that means that these indices here need to be space-time indices instead of a time index and a spatial index. And so let's look at them first in pairs, this pair and then that pair. This pair, the spatial indices, well, it's worth noting that in the local Lorentz frame, R0, 0, 0, 0 is equal to 0, and similarly R up 0, 0, 0, 0 is equal to 0. Why? By anti-symmetry on this pair or on that pair, either one of them. If you interchange this pair of indices, you should flip a sign. The only number that is equal to itself when you flip its sign is 0. Okay, so this has got to be 0. And that means that I can rewrite this still in my local Lorentz frame as R mu 0 mu 0, summing over all the indices. All I've done is added on this term. This term vanishes. So I've gotten part way toward having a geometric relationship. That is, I'm now summing not from j equal 1, 2, 3, but instead on mu equals 0, 1, 2, 3. So in the local Lorentz frame, Newton's field equations can be written in a local Lorentz frame in a nearly Newtonian situation. They can be written in that form. But we have the additional problem here that we have no indices on the right and we have 2 0 indices on the left. Okay. Oh, I should note that this is the Ricci tensor. I've summed on the first and the third indices. So this first guess is, again, in a local Lorentz frame. We know, in fact, that this is true. This is just rewriting Newton's field equation in Einstein language. In a local Lorentz frame, you take the Ricci curvature tensor, you take the time part of it. That is 4 pi g times the mass density. So it's a reasonable guess then, I would think, that we can guess that in general, the Einstein equation should say R alpha beta is 4 pi g times, in place of rho. So I'm guessing a geometric frame independent relationship that would include this as a consequence, okay? But I want this to be R alpha beta, so for the full Ricci tensor, it should be equal to 4 pi g times something that has the property that T00 is equal to the mass density in a Newtonian situation. So the guess is that the Ricci tensor is 4 pi g times some analog of mass density whose time component is equal to mass density in a Newtonian situation. Well, I'm going to let you read about this quantity. I'm not going to lecture about it, at least at this point in the course, but just leave it for you to read about that. This is, in fact, something called the stress energy tensor. It's a tensor that has the property that in a local Lorentz frame, T, let me put the indices up in a local Lorentz frame. I raise this zero index, I flip a sign, I raise that zero index, I flip a sign again, I get back to where I started. So T00 is equal to the total density of mass energy, including all forms of energy, rest mass, kinetic energy, thermal energy, magnetic energy, and so forth. T0J is the energy or mass energy flux. Tj0 is the momentum density, for momentum density. And Tjk is the stress tensor, which most of you will have met somewhere or other in your education. Some of you may not have. But it is for situations where you may have shear stresses, it's the analog of the pressure. It's the force per unit area acting across some surface. And again, I will let you read about this in the reading if you're not familiar with it. And so our guess at this point is that the Einstein equations should say that R alpha beta is 4 pi g times T alpha beta. Ricci tensor, aside from some multiplicative factor, is equal to stress energy tensor. The dominant part of the stress energy tensor in a nearly Newtonian situation is the time part, which is mass density. Energy fluxes, because in a Newtonian situation, mass moves at very low velocities. The energy fluxes, if you set the speed of light equal to 1, which I am doing, and I'm going to let you read about using units where the speed of light is equal to 1 if you don't feel comfortable with that. If you set the speed of light equal to 1, then energy flux and mass density have the same units. Energy and mass have the same units. E equals mc squared, c is 1. But the energy flux is tiny compared to the mass density. The momentum density is tiny because of low velocities, and the stress is tiny compared to mass density. So the dominant piece of the stress energy tensor in nearly Newtonian situations is this piece. And similarly, in nearly Newtonian situations, the dominant piece of the Ricci tensor turns out to be this piece. And the Einstein field equations then reduce to that, and then the rest of the Einstein field equations in a local Lorentz frame are just negligible. They have tiny values on either side of the field equations. Okay. So that is a guess, and Einstein made that guess, I think already in 1912 or 13, something like that, and it's wrong. And he struggled for about 3 years to understand why it was wrong, what the problem was. And I'm going to say now what the problem is rather quickly and what the solution is. The problem with this version of the field equations is that when you turn it into differential equations for the metric coefficients, you have too many equations. And so these are a set of field equations that basically have built into them some self-inconsistencies. So let me make that more precise. Recall that the Riemann tensor looks like a metric with two derivatives on it, plus nonlinear terms. And so when you contract on the first and third slots, you get a Ricci tensor that also has this same property. It's a metric with two derivatives on it, plus nonlinear terms. And so this Einstein equation, this proposed Einstein equation, in fact, is a set of 10 then partial differential equations for 10 components of the metric. Why 10? Because the metric is symmetric under the interchange of alpha and beta. And so it's basically a symmetric 4x4 matrix, if you want to think about it in matrix language. That means it has 10 independent components. And similarly, the Ricci tensor and the stress energy tensor turn out to be symmetric and under interchange of their slots. And so again, so here you have 10 equations, which are partial differential equations for 10 components of the metric. Now you might say, well, how can that be a problem? And that's what Einstein thought at first. He said, well, I'm quite happy with that. But it is a problem for the following reason. That we have the freedom to choose the coordinate system in which we write down these equations, in which we take this geometric relationship, turn it into partial differential equations for the metric coefficients by writing the Ricci tensor in terms of the metric. We have a freedom of our choice of coordinates. And we have 4 free functions in that freedom. So we can adjust however we wish. X naught is a function of time. X1 is a function of time. X2 is a function of time. X3 is a function of time. We have complete freedom to adjust those. Well, we better do it in such a way that the coordinates are non-singular in the region we want to work in. But we have enormous freedom. And you can show, by working with this coordinate freedom, that you can use this to make 4 of these metric coefficients be whatever you want. Make 4 of the 10 G alpha betas viewed as functions of coordinates be whatever you want. And for example, one often likes to adjust the coordinates so G00 is -1, and so G01, G02, G03 are all 0. And you can do that by adjusting your coordinates. You just change the shapes of the coordinate lines appropriately. You can do it. But this version of the field equations doesn't allow that. You've got 10 equations which must all be satisfied for 10 unknowns, for 10 G alpha betas. And so there's a fundamental flaw in that version of the field equations. And one has to go back to the drawing boards and find a new version of the field equations that will have the property that there are 6 equations for 10 unknowns, 6 equations for 6 of the metric coefficients, and you're free to choose the remaining metric coefficients however you wish, like I have just discussed. And so that's what Einstein struggled with for a long time. And he found the solution, and independently, almost simultaneously, Hilbert found the solution after Einstein went and spent a number of days talking with Hilbert and Hilbert's research group about the problem. Then Hilbert started really thinking about it seriously, and the two found it more or less independently, but only because Einstein had discussed it at great length with Hilbert at the time he was struggling with it. And the answer is the following, that by virtue of the Bianchi identities, which I mentioned to you before, which say alpha, r, alpha, beta, gamma, delta, semicolon, epsilon, plus 3 terms like this where you're permuting the last 3 indices. It turns out that this implies that if I define something that is now called the Einstein tensor, which is the Ricci tensor minus 1/2 the scalar curvature times the metric. So it's basically the Ricci tensor with one other term thrown on that involves the scalar curvature. Turns out that the Bianchi identities say that this Einstein tensor has vanishing divergence as an identity. So this is a remark, okay, that is a key to getting to the correct Einstein equations. A second remark, which is something that you will read about if you don't already know it, is that in flat space-time, in a Lorentz frame, the energy conservation just says d mass energy density with respect to time plus the spatial divergence d of the energy flux is equal to 0. That's obviously a standard conservation law, and that's conservation of energy, since this is energy density and that's energy flux. It says TdTj0, which is momentum density with respect to time, plus dTjk, which is the stress tensor, which turns out to be identically the same thing as momentum flux, as most of you will know, but you can read about if you're not familiar with it. This vanishes. Or equally well, it says that T alpha beta comma beta is equal to 0 in a Lorentz frame in flat space-time. This equation involves only one derivative, not 2, so there's no subtleties, no dangers about when you have only one derivative. So in curved space-time, in a local Lorentz frame, this must be true. But that statement in a local Lorentz frame in curved space-time is just the statement, the geometric frame independent statement, that the divergence of T vanishes. That is, in a local Lorentz frame in curved space-time, this semicolon would be the same as a partial derivative in a local Lorentz frame. So this would reduce to that. So this is a geometric frame independent expression of the conservation of energy and conservation of momentum. So these two equations are already satisfied before you go in and you ask yourself about the Einstein field equations. And so if we choose, let me put it differently, it therefore seems quite reasonable that nature may have chosen to have field equations that determine the nature of the space-time curvature. Okay, yeah, sorry. So it seems quite reasonable to expect that the form of the Einstein equations will be the following: that G alpha beta is equal to something times G times T alpha beta. So some number here, and you need to go to the Newtonian limit to get that right. And when you go to the Newtonian limit, you find this needs to be 8 pi in order that in the Newtonian limit you wind up with this as a consequence. Okay. If this is what you choose to be as the field equations, so this is the second guess, then in fact, before you ever imposed them, you already knew, before imposing these field equations, you already knew that G alpha beta, semicolon beta, was 0. You already knew that 8 pi G T alpha beta, semicolon beta, was 0. So you already knew that these guys were equal to each other. This is 0, that's 0, so these are equal to each other. These are 4 equations because there's one free index, alpha. And these are 4 equations that are just derivatives of our proposed field equations. And so it turns out, in fact, then, that what these are 4 identities that are already satisfied, that the divergence of this is the divergence of that, before you impose the field equations. And those put 4 constraints then on that say that the field equations are only giving you 6 new pieces of information. That's what you need in order to have a well-posed theory. So this is basically how Einstein got to a well-posed theory, and a theory that has been brilliantly verified by experiment. Okay, so I will talk about gravitational waves then on Monday. Finally, we will get into it. I hope to do it today, but I didn't quite.